To start the day, I would like to tell you a bit about the agenda. I will start about telling you a bit about the challenges of the current systems. What kind of needs do we have to meet? What kind of characteristics do we have of energy systems today? Then I will go into smart energy systems. What exactly is that? What does it comprise of? What are the characteristics of such a system? And I will end up with a case study bringing this smart energy system to life, showing how such a system could look like, what kind of components we have in it, how we can control it, and how we can have a security of supply. Here we have a very simple overview of the current energy systems. On the top you can see a typical electricity system where we supply electricity and heat from a power plant. We have a fuel consumption, and we see we use about 173 units of fuel to provide 30 units of electricity, 40 units of heat, 30 units of transport. Maybe you want to remember that, because I'll come back to that principle diagram a few times. So just note what kind of fuel inputs we have. We can make a very simple improvement to that, so we can go from France to Germany. For example, when we go down to the traditional system, we separate the electricity supply from the heat supply. So we just provide the heat with a fuel boiler, and the power plant provides then the electricity. We still have the transport demand, and you see there's a bit of refinery losses there, but we can actually save 40 units of fuel just by moving countries like that, or by changing the energy system very simply. So this is just something to remember, that that's where we are. As you all know, I will not tire you with reasons for reducing the dependency of fossil fuels. I will remind you of greenhouse gas effects, security of supply, geopolitical issues, and also, of course, the whole socio-economic issues about importing fossil fuels, or and the balance of payment of different countries, and the dependency that can create. But we want to decrease the use of fossil fuels for a number of reasons, but we do have some challenges, because the current system is extremely flexible. Whenever we turn on the light, somebody will shove in some coal, some oil, or some natural gas, and we will have the electricity we need right away, or the heat boiler can be turned on automatically if we turn on the heater, because we have a highly dense fuel, high density fuel that we can simply use of all the time. Then the idea, if we want to keep that flexibility, we could change all the fossil fuels to biomass. But that's not possible either, because if we just replace fossil fuels with biomass, we will simply not have enough biomass to cover that demand. So we need something else. We need to use intermittent resources. We need to use wind power. We need to use wave power. We need to use photovoltaics. We need to use solar thermal. We need to use geothermal. We need to use all of these resources that are a bit hard to handle. We can also do that in these systems that we see here with no problem, at least to some extent. So here you see the same two systems. So we take I'll just, to make it very simple, the top one is the French system, the bottom one is the German system. But we have the electricity system. We can increase the wind power to 25%, save a lot of fuel, going from 170 to 140. And on the bottom there, we can see in the German system, if we start to implement 25% wind, we can go from around 140 to 120. But there's a limit to how much wind we can integrate in this way. There's a limit to how much we can do with the current system design, and 20 to 25% is the limit that we can go to. So if we want to replace more of these fuels that we need here, then we need a new system design. Of course, these diagrams are very ideal, and I'll come back to some analysis dealing with a not ideal situation. But let's go back to some basics. We want to save some fuel, that's the whole idea. So here we have four kinds of energy systems without any intermittent resources. The top ones are the electricity system and the traditional system where we've separated the electricity and heat supply. But we can improve on that a bit. We can go to the CHP system or the combined heat and power system. It can also be a combined cooling and power system. But just by doing that, we are able to reduce the fuel consumption in such a system even more, even without putting in any intermittent resources. So we need to remember to design our system in a good way. We can also have an integrated system where we use a heat pump, and if we have an external heat source, we're able to reduce the fuel consumption from 170 to 100 and save 70 units of fuel just by redesigning the system. So when we introduce intermittent renewable resources, we also need to redesign our system. And if we take the same principal diagrams of these four systems and introduce 25% wind power, we can see that we are able to reduce all of the fuel consumptions by another 10 to 15%. But still there's a limit. I will try to now explain some of the technologies that we could use in these systems to increase from the 25% to even more, because we need to save more fuel than that if we want to limit the fossil fuel consumption and the biomass consumption in the future. I've taken one example of our studies. It's a technology study where we have evaluated 7 different integration options. What you see here is an excess electricity diagram. On the x-axis you see an increasing amount of wind going from 0 to 50 terawatt hours, or 0 to 100% of the electricity supply. And on the y-axis you see the excess electricity production, so meaning when we put in a bit more wind, how much do we have to curtail? How much can the system adopt? And if we go to, for example, let's go to the 30% or the 50%, and here we see that we have to curtail maybe 7 terawatt hours if we put in 25 terawatt hours of wind. So this is the principle here. We show if we increase the amount of wind, how much do we have to curtail? And behind this, there's hour-by-hour analysis of how this system is actually working. What happens when the electricity demand is high or low compared to when the electricity production is available from the wind power, compared to what happens in the heating sector. The diagrams that you see, or the lines that you see are 2 different systems. The light gray one is an energy system with a CHP plant, where the CHP plant does not regulate. So if we just go back to this one here, we see if we take this system here, we have a CHP plant that operates according to the heat demand all the time, so without taking into account the wind power. The darker gray one is where we have CHP regulation. So we make sure that the combined heat and power plant does not operate at times where we have wind production. How is that possible? Well, that's possible if we have a heat storage. So if we go back to this one again, we take the CHP plant here, and then we have a heat storage here, and then we're able to disconnect the heat consumption from the electricity production from the CHP plant. And you can see on these diagrams that we are able to increase the integration of renewable energy sources if we make the CHP plant produce electricity when the wind is not blowing. Also, you can see we can go to maybe 12 terawatt hours without having any excess electricity production. That corresponds to 20 to 25% of the electricity demand. Now we have to remember what we started with. The idea of putting up an extra turbine is to save some fuel somewhere in the system. So we want to evaluate not only do we reduce the curtailment of the wind, but what is actually the effect on the primary energy supply, on the fuel input for our energy system. Here we go to the next diagram with the same two graphs, but we still have the same x-axis with 0 to 50 terawatt hours or 0 to 100% wind, but now on the y-axis we have the primary energy supply, and what we can see is that we get a lot of benefit from the first part of the wind that we introduce, but gradually the effect becomes lower because we have to curtail more and more of the wind, and we're not able to stop the power plant from operating or the CHP plant from operating. And you can see on this graph here that if we go to the 12 terawatt hours, this is also where the effect on the primary energy supply decreases. So we save less fuel when we go beyond the 20 to 25% of the fuel consumption, percent of wind in the electricity grid. Now we just look at one situation here. Let's look at 50% wind power. And then let's have a look at a number of different technologies that we could imagine. So here we have the same graph as before here, but we just look at one situation, namely with 25% of the annual electricity production covered by wind. We have 7 integration options in this diagram, and these options are electric boilers for district heating, large heat pumps for district heating, hydrogen for CHP plants, hydrogen for micro CHP, hydrogen for vehicles, battery electric vehicles, and flexible demands. Looking at the graph again here, we can see the marginal excess electricity production when we introduce 25% of wind in this system. And we can see how much we can then save with these different options. Now, of course, they are comparable in the sense that they have the same magnitude of capacities. Now, there are different characteristics of these different technologies, but in order to compare them, we need to either evaluate it on an economic investment, the same economic investment, or the same capacity. Here we have the same magnitude of the capacities compared to each other. What we can see here is that the electrolyzer producing hydrogen for the CHP plant, number 3, is the best option for integrating or for reducing the excess electricity production. The other 3 that are pretty good are the electric boilers, the large-scale heat pumps for district heating, and then the battery electric vehicles. The ones that are not very good at reducing the excess electricity production are the flexible demands and the hydrogen for vehicles. And why is that then? Well, maybe it's because of the type of intermittent resources that we have in such a system, or the characteristics of the intermittent resources that we have. Because wind does not have a daily period. It has maybe 2 weeks of a period. So we need some other flexibility than these very short-term technologies, only able to shift maybe from 1 hour to the next hour. Also, the vehicles are limited by the storage of hydrogen for such vehicles. So they're not very good options. But this is then for the reduction of the excess electricity. Now remember, we needed to reduce the fuel consumption. So let's have a look at the effects on the fuel consumption. And again, we look here at the 50% wind power case. So the middle of this graph that you saw before, where we evaluate the effects on the primary energy supply. Here you then see the effects of the different technologies. Now you remember before I told you number 3 was the best option for reducing the excess electricity. But now you actually see that it's not very good at then replacing any fossil fuels or any fuels in the system. It is only able to reduce the fuel in the system very little. If we look at option number 2, the heat pump, then we're able to reduce the fuel consumption quite a lot. And this is due to the fact that we're able to replace fuels in the production of heat using these heat pumps, whereas the electrolyzers producing hydrogen for the CHP plants introduce inefficiency in the system. The same can be said for micro CHP that is also evaluated in this study. If we were to prioritize between these different options, then if we want to save a lot of fuel, so if we want to put up renewable energy sources to save fuel, then we need to prioritize heat pumps, and preferably large heat pumps for district heating. If we look at the transport sector, we need battery electric vehicles because they replace an inefficient internal combustion engine where they're able to reduce the fuel consumption of the system quite a lot. Flexible demands is not as important, and electrolyzers should be on the last priority, maybe with more wind than we have in this system. If we look at the curves, we can see if we increase the wind from 50% to more, then the electrolyzer options do have an important role to play. But we can come back to that. For until 50%, we need to focus on integrating the heat sector with CHP plants, heat pumps, and if we want to do something about transport, then battery electric vehicles for integrating renewable energy is by far the most feasible option. Now, this study here shows how electrolyzers should not be used to produce fuels for a CHP plant. We have other studies that show the same, but it actually means that we should avoid all kinds of direct electricity storage if the aim is to put it back onto the grid as electricity. If we have any other options than to produce or to store it in a battery and put it back on the grid as electricity, we need to do that. It is not a good solution to introduce a round trip as long as we have an oil boiler somewhere in the system, as long as we have an internal combustion engine somewhere in the system. We should avoid to have round trip losses. We have started this transition in Denmark. We have used the combined heat and power system and introduced a lot of wind power. Actually, we have 35% of wind power in the Danish electricity mix. Due to the combined heat and power system and this wind power, we have been able to keep the primary energy supply constant, illustrating how the principal diagrams that I showed before can be applied in real life and has been applied in real life. And also this is meant, of course it's not only the CHP plants that are the cause of the constant primary energy supply, but it has a major role, as I showed you in the principal diagrams before. But let's go back to the 4 principal diagrams where we now have introduced these 25% wind. We have down here the Danish situation where we have 35% wind power already. Up here we have the German situation, more or less. Not a lot of CHP, but separated power plant and boiler production. So I would suggest that Germany moves down to this one here, not introducing a lot more wind maybe, but just changing their system, or doing both the more renewable energy, intermittent renewable energy, and changing the system at the same time. Now I have a small animation. Look at that. Just again, one more. Yeah, I'd have to show it 3 times because I spent so much time on it. So the point is, we have to move from this system to this system in Denmark. What is this system then? I'll just remove that again. This system here has a heat pump, and it can provide heat for the district heating system. Over here, we have a fuel boiler that provides some of the heat. The CHP plant is not able to provide all the electricity or all the heat, so we need a boiler to provide some of the heat. Over here, we change the boiler to a heat pump. By doing so, we can reduce the fuel consumption, and we can actually increase the wind power penetration quite a lot. Actually, when we look at the analysis, one of them I showed you before, and we have done many others, we can increase the wind power to maybe 40% without having any, while still keeping a good fuel efficiency of the energy system. So let's just look at this district heating a bit. I took an example of a study called Heat Plan Denmark here, because the question is, of course, in the future we may have other options, such as micro CHP or individual heat pumps, and do we want to increase the district heating or not, and what should be the characteristics of that? So the question was, what should we do in the short-term perspective when we want to reduce the CO2 emissions? What should we do in the long term when we want to go to 100% renewable energy? And of course, a lot of studies are behind that, combining energy system analysis and geographical information systems about heat demands in the individual buildings. But the results show that we should increase the district heating to between 60 and 70%. Where we don't have district heating, we should have individual heat pumps. And of course, these individual heat pumps should have the highest COP possible. We have to focus on the synergies in these district heating networks. If we can reduce the house's energy consumption with energy savings, at the same time expanding it, we are able to integrate more of the renewable energy sources. By lowering the temperature, we can use more, for example, waste incineration. We can use more solar thermal. And then there's no reason to make any micro CHP, especially not if we do it in combination with hydrogen, because the hydrogen storage for an individual micro CHP will mean that the power plant would have to operate because the heat demand does not fit very well with the intermittent resources, and the individual storage options are very small. So the integration of the electricity sector and the heating sector should be done with CHP plants and large heat pumps with heat storages and district heating systems where possible, and otherwise we should use individual heat pumps. So that concludes the integration of the electricity and heating sector. But what about the next step? What about the transport sector? What should we do here? In these two principal diagrams, ideal diagrams again, we have increased the wind power penetration to 50%. I don't know, the sharp mind will remember, but this has been reducing the fuel consumption in this integrated system by 15, 16 units just by increasing the wind power, and the heat pump then starts to operate even more. Of course, this is a very ideal situation. But what then happens if we change half of the transport demand to electricity? That's what we see over here. By doing that, we replace internal combustion engines, and we're able to have more wind in the system. Actually, we're able to go even beyond 50% wind power. And by doing so, we can see that it has a very large effect on the fuel consumption. We can go down to around 60 units. So we save around 10 units by replacing half of the transport sector with electric vehicles. What about the rest? Here we can see the same system as we saw before, 50% wind power, 50% electric vehicles. But now I just changed the name because the losses are almost the same. But this is then, we imagine that the rest of the transport demand is covered by first generation biofuels. Now that's not a very good idea because of a lot of reasons, but predominantly land use reasons and the connection to the food production. So we're going away from the first generation biofuel. So what should we then do? Let's go to the second generation. Uh-oh. Look at that. Let's go back again. Just try. Look at the fuel consumption. 59. Wait. 80. Damn. What happens down here is, if we take a second generation biofuel, imagine that there are 60% losses. This is a typical second generation bioethanol plant where we put in, or we lose 60% of the input. Then all of a sudden, we're back from where we started almost. We're back to 80 units of fuel in. Now, of course, we can start to use some of the waste products, but it just shows you there are really great conversion losses here. So what should we then do about that? Well, we have an idea. First of all, let's look at these biofuels. In this study here, we've looked at 1 petajoule of biofuel and 1 petajoule of electricity, and a lot of different biofuels actually. And what we can see is that to produce 1 petajoule of biofuel or fuel, the electricity production from wind power, even from wind power parks, which this represents, has a much lower area impact or land use impact than all the biofuels that we can imagine. So what should we then do? Well, this tells us that we should go to electricity consumption. Like the diagrams I showed before, with the electric vehicles can reduce the fuel input. Also, we can see that if we evaluate the different biofuel options, electricity from a land use perspective is much better. What we then tried to do was to map the transport sector to see what are actually the characteristics of the different transport demands. How much could we replace with the public transport? How much could we replace by doing by putting in electric vehicles? What are the habits of the different transport demands, from personal vehicles to goods? And by doing so, we were able to make some different scenarios for the Danish transport system in 100% renewable energy. Now, this is a part of a study called CESA. You can see the name here. It's called Coherent Energy and Environmental System Analysis. And in this study, we evaluated the transport sector quite thoroughly. And what we found was that we have to decrease the growth in the transport demands. We have to invest in modal shift because it's more effective. But most of all, we have to go to direct or indirect electricity consumption. And we can cover maybe half the demand by doing so, because a lot of the personal transport we can cover by either battery electric vehicles or hybrid battery electric vehicles. But what about the rest? What should we do? Because we have quite a lot of trucks still, we have ships, we have aviation. And these types of transport we cannot put in a battery, we cannot cover with a battery or put on all of it on rail. So we need to have some kind of fuel to cover this. And we just saw the second generation biofuel is not really a very good idea. So we identified 4 different ways or options of creating liquid fuels for transport. I will not go through all of them, but what we are able to do with these 4 principal options is to combine the carbon sources that we have in biomass with hydrogen produced from intermittent resources and create some liquid fuels. And there are different options for doing so. This is one of them. It's called hydrogenation of gasified biomass. What you see over here is 100 petajoules of methanol. What you see over here is 75 petajoules of biomass. And if any of you know second generation technologies, it would not be possible to have a lower biomass input than the biofuel output. So how is that possible? Well, we use quite a bit of electricity here for producing hydrogen. So we gasify the biomass, combine it with hydrogen from electrolyzers, and make chemical synthesis to create methanol. Now, this is not really very high tech. We can already do that now. It is actually being done now. You can go to Iceland. Does anybody know the Blue Lagoon? Just next to that, there's a methanol producing facility using CO2 from the ground to create methanol. This is not fantasy. It is not high tech. Well, it is a bit high tech, but it is not unknown territory. It's not unknown technology. We can go and buy these components. Of course, we can do it more efficiently in the future. So this is what we suggest. From CESA we have a message here. We need to identify and analyze pathways which enable us to transfer electrons from wind power and PV to synthetic liquids or gaseous fuels for transport. So we have done that, and we have tried to integrate it into an energy system. And you can see the energy system here. Over here you see a transition from today to 2050, where we have implemented all of the components that I have gone through today, except I haven't mentioned a lot about energy savings. Energy savings is, of course, extremely important. But in this scenario here, we have tried to integrate the transport sector in the way that I have described, creating this kind of liquid fuels. And we're able to meet these demands by the residual resources we believe to have present in Denmark. Let's go back to this one. So now we try to make these synthetic fuels. So we still have 50% of the transport sector covered with electric vehicles. Here. But now the rest we cover with synthetic fuels. And by doing so, we can actually reduce the fuel consumption to 62. I don't know if you remember before, with the second generation biofuel, it was 80, the fuel input over here. But the characteristics of this system means that we can actually increase the wind power penetration. So now we can go from 50% to 75% or even more, but in this principal diagram we have 75%. And by doing so we can come down to a fuel consumption of maybe 40 in this principal diagram. I don't have a cartoon on this one. So, this is then the CESA study. This is the real deal. This is where the hour-by-hour energy system analysis have been performed. This is the study that brings this smart energy system to life. What you can see in this Sankey diagram is that in the middle the electricity supply is present and is really the backbone of such a system. But you also see how it's interconnected with a lot of other things in the energy sector. Now most of these things are known technology. They're not rocket science, but it's something that we have to do if we want to have a fuel efficient system. What we can also see here is that the transport sector is heavily integrated in this system. Okay, let's look at some of the components in this electricity, in the electricity system that we have here. Over here you can see the capacities installed on the electricity side. That increases quite a lot. Of course, if we want to introduce the 85% intermittent resources we have in the CESA study, we need to increase the intermittent resources. Predominantly, we have installed wind power here. This represents the capacities. What we need also are the CHP plants and the power plants. And actually, we can see that when we don't have any intermittent resources, we can cover the demands with the same amount of capacity that we have today. If we then look at the production, now this is the terawatt hours, the actual production, we can also see that the power plants produce very little in such a system. So they go to maybe 10 to 15% of load factor. So we need to have a system where the power plants do not operate a lot, but where the wind power and PV and wave power are actually able to provide most of the energy. What happens then on the consumption side? Well, quite a lot happens on the consumption side, because as you can imagine, in such a smart energy system, we need quite a lot of flexibility. And we've already integrated both the electricity and transport sector. So what we see here is the electricity consumption. And the sharp listener will see that we go from 35 terawatt hours here in 2010 to 70 terawatt hours in 2050, or even more. Now this is not because we have not saved on the consumption that we know today, But this is because we have integrated the heat sector and we have integrated the transport sector. So we need a lot of electricity for especially these synthetic fuels that we put in. Just skip this. So, what can we do on the demand side? Well, you already saw the electricity consumption. But what we can do is we can look at the different grids of such a system. You saw a bit of it in the Sankey diagram. We have smart electricity grids where we are able to combine heat pumps and electric vehicles with the intermittent renewable energy sources. We have the smart thermal grids where we are able to flexibly integrate heat production with thermal storages, also using other sources for the heat supply. The last part is the smart gas grids, and the gas grids enables us to store gas actually over very long periods. I did not tell you a lot about that, but I will tell you about that at my lecture tomorrow afternoon. Gas storages, gas grids. Very important part of the smart energy system. Now, concludingly, large-scale integration of intermittent resources require integration, regulation of CHP plants and heat storages makes it possible to integrate 20 to 25% wind power and a lot of CHP production. Adding heat pumps and heat storages can increase this to 40%. Adding the transport sector can increase the intermittent resources in the electricity grid even more. And also, again, please avoid any kind of electricity storage. Transport demand should be met by electricity, but we need some kind of synthetic fuels in order to reduce the strain on the limited biomass resources. If we use the principles that I showed you before with the gasified biomass and the hydrogen, we are actually able to decouple the whole system from biomass. Because what we require really is the carbon in the biomass. So if we have another carbon source, we can reduce the biomass input even more. So this is also a long-term strategy to phase out biomass even more in such a system. Because the infrastructure that we have then installed will facilitate that we have much less biomass in the future if we have a biomass resource. So let's see. What are the current challenges? Well, the current system is extremely flexible. With this system here, the smart energy system, we have created the same kind of flexibility that we have in the current system. Of course, it is a little more complicated to operate such a system, but it is not more expensive. If we look at the costs of it, it is not more expensive than the system we have today, except when we start to lower the biomass consumption and introduce more hydrogen, it will increase the costs. But we can find levels where it is possible to cover it with the biomass that we have. We create the flexibility by creating the liquid fuels, using the gas storages, using the thermal storages, using the batteries in the electric vehicles. And then we're able to actually integrate all of these intermittent resources that we thought was a problem on the first slide that I presented. I think with those words, I will stop now. Let's see. Yeah.
thank you very much, Brian, for that excellent presentation. The time already is quite advanced. Nevertheless, I would like to allow 2 questions in order to start a discussion. And I'm sure Brian will be later here also in the coffee break and continue discussion. And before you then go to the coffee break, you also will have the presentation of the poster session.
Hi, my name is Martin Hindel. I'm from France. This is maybe not the best. I have 2 questions. The first one is more to politicians. What is the cost increase of the electric grid and heat grid with the integrated system? And the second question is regarding alternative CO2 sources for synfuels. I hope those have to be renewable sources, because if they're fossil fuel, then we're in the same situation that we started from.
Well, we're just starting with the thermal grids. Thermal grids may have the same or even lower cost than we have today. We have concluded quite a lot of analysis analyzing whether we should have district heating. And when we look at the costs of those and compare it to the individual solutions, then we can see that it is more feasible to have the collective thermal grids compared to the individual solutions. Even when we go to insulate the houses, we will still have a unit cost in each houses. You will still have to go and have a shower sometimes, and there will still be some kind of heat or cooling demand in the individual house, where you will have a cost for the unit you place in those houses. Compared to that, the thermal grids are a long-term investment that creates also the possibility of including much more cheap heating options than the individual solutions that would typically be provided by a fuel or an electricity consumption.
But is comparing to the individual source situation relevant for Denmark, where you already have 46% district heating? Are you not increasing the cost of that district heating?
I'm not sure I understand.
You're saying compared the integrated district heating system, we call this, is still cheaper than the individual solution.
Yeah.
For Denmark, that is no longer.
Well, we have done a European study where we have made the same kind of conclusions. We are able to reduce the costs of the European system if we start to implement district heating on a very large scale in Europe. Because when you imagine you have a house and there's a house next to it, and in Europe there's a lot of houses next to each other, then you start to realize that the costs of the individual solutions are much higher than if you have a thermal grid. It's funny how you cannot cooperate from the heat supply, but you can cooperate on the electricity side.
And the cost increase of electricity?
You were talking about the electricity grids, both. If we take the production of intermittent resources, of course, if you curtail, it will be more expensive. But if you start integrating and doing what I showed you here, saving fuel, then you'll save on buying fossil fuels or biomass compared to integrating the wind. So when you start to change the system as well, then it starts to become feasible. I can show you.
The global approach, yes, but what about the individual consumers? Individual electricity, because that's what politicians are looking at, right?
That requires a longer answer than I think we can do now. But in the Danish system, it has increased the cost to have 35% wind power. It has increased the cost by how much is that? 1 øre. What is that? 0.07. Yeah, 0.07 cents. I don't think it's a consumer problem. It's more a public regulation problem.
Final one.
As far as I understand, Germany is promoting wind PV, but also recently storage system. While maybe I know something storage system are not in your smart
It's hard to squeeze in all of the details in a speech like this, but we do have, I think it's 10 to 12% PV coverage. So photovoltaics covers more than 10% of the electricity consumption, and solar thermal covers more than 10% of the heat consumption as well. Both individual solar thermal and large-scale solar thermal for district heating. So it is included, and it is a very important part of this system as well.
So thank you very much again. And then we continue discussion in the coffee break. And now we get over for the coffee